particle. Kind of crazy stuff. All right. And then the last one, number 3. This one's nicer. This one's a little more. I like this one better. So this is 2 air pucks collide at a right angle to one another. So they come in and they stick, and then they slide off. Each has a mass of 300 grams. One air puck is traveling at 3 meters per second, the other at 6 meters per second. Relative to a coordinate system, you're choosing to determine the magnitude and direction of velocity of the stuck together pucks after collision. Also report your answer in vector notation. Vector notation is super nice actually for all of this, but it's kind of nutty. I'm not going to cover it actually. I'm going to skip that part of it. So these problems are hard, but I will admit they're kind of tedious in terms of having to slog through all the math, all the algebra, and all the writing more so than anything. So 2 air pucks collide, stick together. So we got one coming in here, one coming in here. They're going to hit each other, right? And they're going to slide off. All right. So I'll make it some amorphous thing here. So each has a mass of 0.3 kilograms. All right, so the first one, 3 meters per second. This is 6 meters per second. All right.
Isn't there 2?
Yeah. What? Would you like to come draw for me?
Alright.
You sure?
Yeah, I'm good.
Positive?
I mean, if you insist.
No, I think I'm right. So the total mass of this new object is what? 0.60 kilograms. So P initial x equals P final x. Well, the initial x momentum is all in this one, right? So 0.30 kilograms times 3 meters per second, and it's positive 3 meters per second. So 0.3 times 3 is, what is that? 3 times 3 is 9, 0.9 kilograms times meters per second. Final momentum, final x momentum, well, it's going to be the combined mass now, 0.60 kilograms times the final x velocity. So we can go right through, get the final x velocity here. All right, that's the total initial momentum, total final x momentum. All right, so the speed we'll see. So we get 0.9 kilograms times meters per second divided by 0.60 kilograms. The final x component, 9 over 6, what is that? That's like 1.33. 1.5, yeah, duh. 1.5 meters per second, and it is positive. And it's half of the initial x momentum, right? Because we doubled the mass of this object, basically. So the x momentum, the x velocity is going to have to be cut in half. You can pretty much think of the same thing in the y direction here. So now, P initial y equals P final y. All right, so we've got just the 0.30 kilograms times the initial y velocity here. I'm going to make negative 6 meters per second equals 0.60, our new combined mass, times our final y velocity. All right, divide both sides by 0.60. Right, P final y. Looks like it's going to be 3 meters per second, negative 3. Right, we've cut the velocity in the y direction in half as well. Because again, we doubled the mass. You know, each component has the velocity is going to be cut in half. So we put it all together now. Right. Alright, we put these all together and look at this. So this new 0.60 kilogram object moving with a y velocity of negative 3.0 and an x velocity of 1.5. And I'll tell you something, a lot of kids won't actually bother to calculate the angle because they'll just say it's 45 degrees. But it's not 45 degrees. So the final speed here of the object is, again, Pythagorean theorem. We got to do the two components. So the final speed is the square root of 1.5 squared plus 3 squared. Oh, shoot, this one doesn't put the parentheses on it. I got used to that now. So about 3.4 meters per second. And I guess they don't tell us where to write the angle relative to. So I guess I'll say this angle, call that theta. The angle of motion relative to the x-axis here is tan inverse of second tan of opposite over adjacent, so it's 3 divided by 1.5. I get an angle of about 63 degrees. Now, why does it make sense that that angle is bigger than 45, just kind of conceptually?
The y direction is faster.
Yeah, the y direction is faster. Yep. So there's more y momentum initially, so there's got to be more y momentum afterwards there. So this is my favorite question here. This is the one that, you know, kind of the most doable / easiest to kind of see. Just they stick together and slide off together. The explosion one, you know, we kind of were able to figure out kind of conceptually what it would look like. Math is annoying. The billiards ball one is also pretty decent. You get that deflection angle, pretty shallow, doesn't lose much forward momentum. Since it doesn't lose much forward momentum, that ball that you're going to send up toward the side pocket doesn't gain much forward momentum. You know, so it goes steeper than 45, just kind of goes up a little bit. So that's really it. There's nothing new here in terms of the concept of conservation of momentum, just that you've got to keep track of the x direction and the y direction separately, okay? So tomorrow I'm going to post a review sheet. It will be another multi-dimensional motion question and just, you know, a couple more functions questions like the quiz. You know, I'm just trying to drive this home, this momentum stuff home, because this is a topic that shows up in the AP exam quite a bit, momentum in general, between the functions and collisions. All right, stop this here.